Assalamualaikum and very good morning. Okay, so this is the power factor correction subtopic. So actually power factor, which is the angle, the cost function of the different angle of the theta b minus theta I is a very important parameters in power delivery. And we all know that the power utility, which is in Malaysia, which is a TNB, they will charge the energy utilizations by the consumer in terms of kilowatt multiplied with the hours. Okay, so that's why kilowatt hour, which is equivalent to joules. Okay, and which means that the energy charge is based on only on the average or real power, which is P. Okay, so no Q is used to actually calculate the bills. Actually, so what is the importance of the reactive power? The Q. So actually the reactive power, the Q, is important because it contributes to the power factor. How it is contribute? So we refer to the power triangle. So as you know, we have P and we have Q. Okay, so this is your power factor. So if your Q is very low, meaning that the power factor is very high. Okay, the power factor is very high. But if your Q is very high, meaning that your power factor, the difference between voltage and current will be very the difference which is very high, which means reflect that the power factor is very low. So we always want the power factor to be always high. Okay, sorry, the power factor to be very high, which means that the different angle is minimum. Okay, so that is the importance of Q. So Q, the value of Q will determine the angle, okay, the power factor. If the power factor is not unity, so the ideal power factor is unity, it's always unity. We want, the target in the power system is to have the power factor is always unity, meaning that the voltage and current are always in phase. Okay, but if the power, but usually it cannot be done. Okay, it's very impossible because the load is not a resistive load. It's actually a combination of inductive or maybe capacitive load. Okay, so if the power factor is not equal to unity, meaning that the current that draws from the source is always higher than the load demand. Okay, and this is not efficient because usually the losses is very high. It's actually what you call is proportional with the current that flow inside the cable. So if you have higher cables multiply with the internal resistance of the cable, so it will actually produce losses. So in order to actually increase the efficiency by reducing the losses, you need the power factor to be as high as possible. And this can be done by using a correction, what we call the power factor correction. And this can be done by simply putting what I call a capacitor. Why capacitor? Okay, why capacitor? You may ask, why capacitor and not inductor? Because our load, our typical load or practical loads are actually inductive in nature, such as the motor, which is our fan, okay, our blender, our washing machines, that related to what we call rotation is actually a motor. And a motor, as we can see, is a winding. Is actually the construction of the motor is the conductor winding. So any conductor that is wind up, okay, is like a solenoid. And solenoid, we know that is actually a basic structure of inductor. So anything that is a coil, so it will produce induction. Okay, so that's why also the fluorescence line and so on. So our typical loads are inductive. So the inductive, we produce a positive Q. Okay, so positive Q. So we're referring to the power angle. So we have P and we have positive Q. Okay, so to actually reduce this angle, what you need to do is to introduce negative Q, right? So this negative Q will actually be deducted from the positive Q, and this negative Q can only be introduced by having a capacitive load. Okay. So this is actually the theory. So when we have higher currents, so draws from the generator, so usually the conductor will be require a very large conductor, which is increasing the amount of copper, and obviously they require increased generating capabilities. Okay. Since the voltage is fixed, which is for home is 240 volt RMS, so meaning that the current is always changing. So depending on the load and depending on the power factor, the current can be very excessive. Okay. So the smaller the apparent power, the smaller the current drawn from the supply. And as you know, the best possible power factor is actually when the angle is approaching 0. Okay, so when the angle is approaching 0, meaning that your power factor is 1. Okay, so this power factor correction is the process of increasing the power factor without altering the voltage or current to the original load. Okay, and so as mentioned before, since our load are inductive, the power factor can be corrected by installing a capacitor in parallel with the load. Consider this circuit. So as you can see, this is inductive circuit. We have R and L, and based on this value, the power factor calculated is 0.707 lagging power factor, and the current that flow inside this is actually 16.97 cos 20t minus 45. And since it's a single loop, meaning that IS is your I out. Okay, and the Phasor diagram can be drawn such as like this. So the voltage waveform is the reference. There is no phase difference. Sorry, there is no phase 0. So the current is actually following or lagging the voltage by 45 degrees, which is cos 45, which is 0.707. Okay, so 0.7 is actually considered as a low power factor. So usually higher power factor is considered as 0.9 and above. So how to actually increase the power factor up to 0.9 or up to unity? This can be done by simply connected a capacitor with a value that we will actually calculate it based on our analysis parallel with the load. Okay, and right now the IS is no longer equal to IO. So the IS is equal to the summation of IO and the I capacitor. And this I capacitor is actually, if you see the equation here, so the voltage across the capacitor is actually equal to the voltage source. Okay, it's actually an imaginary current. Okay, so imaginary current, and IO here is actually remain the same as the original circuit. So if the IO is 16.97, so the current IO here is also 16.97. Okay, the only actually iteration that will be made is on the IS. So the I that drawn from the source. By putting this capacitor, the IS is actually lower than the original IS. Okay, so maybe you didn't have a clear picture. So let's look on the Phasor. Okay, so this is the phasor diagram of the original circuit. As you can see, IO is your IS and is actually lagging the voltage by 45 degrees. Okay, so if you introduce a the capacitor will draw a current, imaginary current, which is 90 degrees. So this is the imaginary current. And we know that the IS is a summation of IC plus IO. Okay, so this is your IC and IO. So if you sum in a vector form, you will have this IS. So the magnitude of this IS is, as you can see, is from here to here is smaller than compared to the original. The original is IS equal to IO, right? So if you measure here IO, which is IS, which is 16.97, but when you introduce the capacitor, okay, so the IS is, the magnitude of IS is reduced significantly. And this is your new, sorry, okay, so that's it, okay, and the value of the capacitor can be obtained by using this formula. Voltage, which is the voltage source, over your IC. And what is ZC? So ZC is actually 1 over J X C, or 1 over J omega C. Okay, usually if you solve the power factor correction using this phasor is quite complicated. Okay, so what we will do is actually by using the power triangle is much easier. Okay, so this is the power triangle for the circuit that connected with the capacitor. So Q1 is the original load. You have P1 and Q1 here. From here, sorry, this is the original, not. Okay, so P and Q. The Q is this original one. Okay, P and Q. Okay, and when you connected the capacitor, so this is your QC negative. So what will happen is actually the Q2. So this one is actually QC. Okay, negative QC. So your Q2 here is actually the Q original minus QC. So it will reduce this one. So the what we call the new power triangle is this. As you can see, the P is intact. There is no what we call alteration in terms of the value, in terms of the load, average power consumed by the load. So it's still maintained. But the Q is right now reduced because we minus the QC. So when we reduce the Q, as you can see, the phase or the angle is smaller. So if the angle is smaller, meaning that the power factor is getting higher. Okay, so Q2 is your new Q, while P is maintained. Okay, so S2 is actually P original plus JQ. And to calculate the value of the capacitor, okay, you can always use the complex power equation, which is VI, we assume that this is V max and IM conjugate. Okay, and we can always also write down VI conjugate over 2 in terms of voltage and also impedance. So this is the equations, V square over 2Z conjugate. Okay, so from that we can use this. Okay, so it's equal to your SC and from that you can get your value of the capacitor. Okay, that is for the power factor correction, and we will continue on example 6. Okay, so a circuit with RL load, so we can maybe draw a circuit which is RL load, and from this load, okay, if that the load absorb 50 kilowatt and the power factor is 0.8 lagging, okay. So, and then the input source is 230 volt. Okay, I think this one is RMS. Okay, usually 230 volt RMS. So I assume this is RMS. But don't worry, because in test or final exam, we always put or identify whether it is RMS or maximum. Okay, but for this example, maybe forgot to put RMS value there. And a capacitor is connected parallel with the load, so that the what I call the total power factor is increased to new power factor is 0.95, so still lagging. Okay, find the capacitor value. So what you need to do first is to find the Q of this load. The Q, and also I think it's better to get all, which is the complex power. Okay, complex power. So from here, the power factor is 0.8 lagging, meaning that your angle theta is the cos inverse of 0.8, which is 36.86. 36.86. Okay, and your what they call the apparent power S is P over cos theta. Okay, so 50 kilowatts over 0.8, which is will give you 50k, but 0.8 is 62.5k. So 62.5k VA, and from that you can calculate your Q. So your Q is S sine theta, which is 62.5k sine 36.86, which will give you sine 36.86 multiply with 62.5k, so 37. So your Q is 37 point, I think 37.5 k var. Okay, so if you draw this, okay, so the Q is right now 37.5k. Okay, the angle is the original angle is 36.86. So if you want to reduce to a new angle, okay, the new angle. So what is the value of the new angle? So from here, the angle is actually cos inverse of 0.95, which is 18 degrees. So 18.19 degrees. And you should note that P is maintained, right? P is always maintained at 50 kilowatt. So no alteration on the P. So right now, what you need to do is to find out what is the Q, this new Q. Okay, what is this new Q, and Q new, and this part is actually the value of your how many QC that need to be injected. So this is your QC, which is negative. Okay. So what you need to do is to find the new Q. Okay, so the new Q can be found by using, okay, what you need to do is, okay, sorry. So what you need to do is to find the new apparent power. Okay, this one, I just put it. Okay. New apparent power, okay, which is S is equal to 50K multiplied with cos 18.19, which is the apparent power is 50K multiplied 0.95, 47,500. So this is your S new, 47.5K VA. Okay, and after you got the S new, then you can compute your Q new. So your Q new is S new sine theta new. Okay, 47.5K multiplied with sine 18.19 degrees. So this should be no problem. So sine 18.19 multiplied with 47.5K. You should get 14.8. So their Q new is 14.8 K var. Okay, so meaning that after you obtain, so you can calculate your QC. So your QC is Q ori minus Q new. Q ori 37.5K minus 14.8K. So you should get around 22.7. I think 22.67K bar. Okay. And you should know that the capacitor, okay, which is your QC, okay, you can actually calculate the apparent power, sorry, the complex or apparent power for the capacitor. Sorry, the complex power, which is 1/2. So this is RMS. Okay, so RMS, so not, it's actually, I think, this one RMS. So we use the RMS equation, so which is VRMS multiplied with IRMS square. Okay, and so VRMS multiplied with VRMS over your is actually XC conjugate. Okay, so since it's conjugate, so you will have VRMS magnitude only square over your XC. Okay, so this one is 22.67K. So this one is actually conjugate. So this one J is actually 90 degrees. So conjugate meaning that this one will become negative J. So this is your QC actually. Okay, QC is negative. So you will find that your XC will be 240 volts square over 22.7 K. Okay, so your XC is 2.5, 2.54 ohm, and we know that XC is 1 over omega C, so 2.54 ohms. So your omega is not given, but it can be calculated because it gives you the frequency, which is 50 hertz. Okay, so your capacitor is 1 over 2 multiplied with pi, multiplied with the frequency, multiplied with 2.54 ohm, which will give you the answer of 2 kali pi multiplied with 50 multiplied with 2.54. Okay, and then inverse. So you have the capacitor value that need to be connected or need to be installed is 1.25 millifarad. So this is the answer. So the answer is 1.25 millifarad. Okay. Next is example 7. A 4 kilowatt 110 voltage RMS load has a power factor of 0.82 lagging. Find the value of the parallel capacitor that will correct the power factor to 0.95 lagging when the frequency or the omega of the circuit is 377 radian per second. Actually, the principle is the same. So what you need to do is to calculate is actually to draw the power triangle. So this is your P. So your P is 4 kilowatt, okay? And the angle here is 0.82. I think 0.82 is actually equal to 36.86, okay? So 36.86 degrees. And from here, I think you can calculate your S, okay, and also your Q. So your S is actually equals, your S is equal to P cos theta, which is 4K multiplied over 0.82. So you should get 4.88. And from that, you can calculate your Q, which is S sine theta, which is 4.88K multiplied with sine 36.86. So this one is 2.9. Okay, 2.9K. And then capacitor is connected parallel with the load to correct the angle. Okay, to correct the angle so that the power factor becomes 0.95. So which is inverse cos 0.95 is 18 something. So 18.13. So this is the new 18.19 degrees. Okay, so this is your Q new. Okay, so same as before. So what you need to do is to calculate your S new, which is from P over cos theta new which is 4K, maintain 4K, and the cos theta nu is 0.95. Okay, S nu. So 4K over 0.95, you should get 4.2. So your S nu is 4.2K. Okay, and from that you can calculate your Q nu. So your Q nu is S sine 18.19, which is sine 18.19 multiplied with 4.2K, should get 1.3. So meaning that your Q capacitor is 2.9K minus 1.3K, okay, which is this one. This is your QC. So 2.9 minus 1.K is actually 1.6K. Okay, 1.6K, and we already know that this is RMS, so you can use what you call this VRMS, okay, over your XC, okay, negative JXC here, sorry. Okay, so negative. So this one is a negative 1.6K actually. So from that, you can calculate your, which is this one, 110 square over 1.6K, okay, equal to 1 over omega C. Then from that, you can get your capacitor. Okay, so I think that's all from me. We'll meet again. Okay, thank you very much. Sorry, this one should be negative also. Okay, negative. So that's why negative should be. Oh, I will check the back. Okay, so but think till we meet again. So I think we have finished the topic 1. Okay, so we will move on. So sorry, this is actually just for single phase. So we will go for what I call a 3-phase system. So thank you very much.